Hello students, welcome to the fourth video on the chapter Solutions. In our previous video, we have discussed certain important concepts like Raoult's law for volatile solutions, where both the solute and the solvent were volatile in nature. On the basis of Raoult's law, we classified the solutions as ideal solutions and non-ideal solutions. The non-ideal solution was further classified into positive deviation solutions and negative deviation solutions. And towards the end, we discussed about azeotrope mixtures. Now we shall move on to our today's class. As you can see here, that today we shall be discussing about solutions with a non-volatile solute. When I say that we discuss about a solution of a non-volatile solute, we can have examples like sugar being dissolved in water, NaCl dissolved in water. There you can see that both sugar and NaCl are non-volatile, whereas water is a volatile solvent. Now here you can see two jars there. In the first jar, I have taken a single volatile solvent. You can see here that there an equilibrium is attained between the vapor phase and the liquid solvent. At this point, the vapor pressure measured is marked as PA0. In the second jar, I am going to add the non-volatile solute. When I add the non-volatile solute, you can see here that the solvent is coming into the vapor state at a lower rate, or we can see that the vapor pressure has decreased for such a solution. From the figure, it is pretty clear for you that the solute has occupied some of the interface point of the liquid and the vapor state. So, the amount of the solvent getting into vapor state has decreased. If we say that at this condition, the pressure noted here is PA, then the relation established is PA is less than PA0. To conclude, when a non-volatile solute is added, it decreases the vapor pressure of pure solvent. This decrease of pressure leads to changes in some other properties of the solvent also. The amount of the change in the value of these property depends on the quantity of solute that is added. Now this concept of how the properties are going to change has been given a heading as colligative property. What is a colligative property? Colligative property is defined as the properties of the solution that depends only on the quantity of the solute added and not on the chemical identity of the solute particles. That means that we know that every pure solvent has got its own vapor pressure, its own boiling point, its own freezing point, and so on. This characteristic property value changes on addition of a non-volatile solute. Thus, by changing the value of vapor pressure, value of boiling point, value of freezing point, and that all depends upon the quantity of the solute added and not on the identity of the solute particle. So, in this order, we have got to learn 4 colligative properties. They are relative lowering of the vapor pressure, elevation in boiling point, depression in freezing point, and osmotic pressure of solution. Let's discuss relative lowering of vapor pressure. As I already explained that how the vapor pressure decreases. Now let's move on to its mathematical expression. If the vapor pressure of the pure solvent is considered as PA0 and the vapor pressure of the solution where a non-volatile solute is added is taken as PA, then according to Raoult's law, we get the relation PA is equal to PA0 into chi A. You already know that it is the mole fraction of the component A. Now, from the mole fraction concept, we have also learned that the sum of the mole fractions of the component is always equal to 1. So, using that concept, we can write chi B is equal to 1 minus chi A. Substituting in the equations, we will get PA is equal to PA0 into 1 minus chi B. That is, we have substituted it in place of chi A. Again, on rearrangement of the equation, we finally get the equation as PA0 minus PA is equal to chi B. PA0 minus PA actually gives you the change in the vapor pressure which has taken place, or this change is what we call as the total lowering of vapor pressure on the addition of a non-volatile solute. As we move on, we can now conclude that the change in vapor pressure is directly proportional to mole fraction of the non-volatile solute which is added, that is chi B. Now, when we see again for the mathematical expression change, we can see here that PA0 minus PA is divided by PA0. Now, when we divide it by PA0, actually that quantity becomes the relative lowering of vapor pressure. That is equal to chi B. Chi B, that is the mole fraction of the solute, you already know is equal to the number of moles of the solute B divided by the total number of moles of the component A, which is the solvent, plus number of moles of B component, which is the solute. On substituting, we can see here that the amount of solute which we usually add is found to be very small, and that itself causes a considerable change in the vapor pressure. So, in the equation, in the denominator, we can neglect NB. So, the equation becomes as chi B is equal to NB divided by NA. NB and NA is the number of moles of the solute and the solvent. And we know how to calculate the number of moles. That is, NB is equal to WB by MB, where WB is the amount of solute which is added, MB is its molar mass, divided by WA by MA, where WA is the amount of solvent which is added and MA is its molar mass. Now, let's do a problem based on this relative lowering of vapor pressure. An aqueous solution of 2% non-volatile solute exerts a pressure of 1.004 bar at the normal boiling point of the solvent. What is the molecular mass of the solute? Jotting down the given data, solvent we consider here as water. Pa0 value is already known to us, that is 1 atmosphere or 1.013 bar. The vapor pressure of the solution, that is after adding the solute, Pa is given as 1.004 bar. So easily, by knowing the Pa value and Pa0 value, you can easily calculate delta P, that is the lowering in the vapor pressure, and it comes out to be 0.009. Now, 2% solution by mass has been given there. What we mean by that? That is 2 grams of solute is present in a total of 98 grams of solvent. So that means we know about the amount of solute as well as the amount of solvent. Now, by using the equation, delta P by Pa0 is equal to Wb by Mp whole divided by Wa by Ma. We can easily substitute the values and we will get the molar mass of the solute B is equal to 41.35 gram per mole. Let's move on to our second colligative property, that is elevation in boiling point. What is a boiling point? You already know. That is, whenever the solution, or if it is a pure solvent, if the vapor pressure becomes equal to the atmospheric pressure, then the substance starts to boil, or that temperature is marked as boiling point. Now, we are considering here a solution where we have added a non-volatile solute. From our previous discussion, we already understood that there is a lowering of vapor pressure. So, obviously, if we have a lowered vapor pressure for such a solution, then we have to increase the temperature to increase the vapor pressure to reach the atmospheric pressure, or in short, we can say that the boiling point has increased, or the colligative property is well understood here that there will be elevation in the boiling point. If we consider Tb0 as the boiling point of the pure solvent and Tb as the boiling point of our solution formed by adding the non-volatile solute, then Tb0 will be less than Tb. A graphical explanation for the elevation of boiling point is shown here. You can see here that first we will consider the pure solvent. You can see here the graph goes on increasing with the temperature, and finally the vapor pressure reaches the atmospheric pressure, and that point is marked as Tb0, that is the vapor pressure of the pure solvent. Now we are going to consider the solution. As already known that the vapor pressure is going to decrease. So the graph starts at a lower point. Here also you can see that as the vapor pressure increases, as the temperature increases, the vapor pressure also increases, and it also reaches the atmospheric pressure. But at that time, when the boiling point is marked here, you can see here that Tb is definitely a higher value than Tb0. Now, this change in the boiling point, that is this amount of elevation in the boiling point, definitely depends upon the concentration of the solute added. Now, to measure the concentration of solute added, we have got different concentration units learned in our previous classes. From there, we consider here the unit as molality. So, you can write that the change in elevation or change in the boiling point or the elevation in the boiling point delta Tb is equal to Kb into m, where m is the molality of the solution, and from our previous class you already know that what is m, that is equal to Wb into 1000 by mb into WA. But here we have come to across a new proportionality constant, that is Kb. The Kb is called as molar elevation constant or as ebullioscopic constant. The unit of Kb is as given here, Kelvin, kilogram per mole. Usually, all these colligative property concepts are used to calculate the molar mass of the solute. So, on rearranging, we'll get the equation as mb is equal to kb into wb into 1000 whole divided by delta Tb into Wa, where Wa is the amount of the solvent, Wb is the amount of the solute, Mb is the molar mass of the solute, and delta Tb is the elevation in boiling point. We shall discuss a problem here. Calculate the molar elevation constant of water. It is being given that 0.1 molar aqueous solution of a substance is boiled at 100.052 degrees Celsius. As usual, let's jot down the given quantities. The molality of the solution M is 0.1 molar. The boiling point of the solution Tb is 100.052 degrees Celsius. Now, since the solvent considered here is water, you can write it very easily that the boiling point of the pure solvent water Tb0 is equal to 100 degrees Celsius. Now, applying the equation delta Tb is equal to Kb into m, we can very easily calculate Kb, which is the molar elevation constant or the ebullioscopic constant, as 0.52 Kelvin kilogram per mole. Actually, this value is constant for water. Let's do another problem. The boiling point of benzene is 353.23 Kelvin. When 1.80 gram of a non-volatile solute was dissolved in 90 gram of benzene, the boiling point was raised to 354.11 Kelvin. Calculate the molar mass of the solute. The molar elevation constant Kb for benzene is 2.53 Kelvin kilogram per mole. Let's jot down the given data first. Benzene, which is given as the solvent, its boiling point in its pure state Tb0 is given as 353.23 Kelvin. Then, the boiling point of the solution Tb is also given as 354.11 Kelvin. The amount of the solvent is given, Wa is equal to 90 grams, and the amount of solute, Wb is equal to 1.80 gram is given. Applying the equation for calculating the molar mass of the solute, you get Mb is equal to Kb into Wb into 1000 whole divided by delta Tb into Wa. We'll substitute all the quantities given there and we get the value as the molar mass of the solute as 58 gram per mole. Let's move on to our third colligative property, depression in freezing point. To understand depression in freezing point, we should first understand that what you mean by freezing point. Freezing point is the point at which we have got the coexistence of the solid state and the liquid state of a particular substance. Or we can say that when the vapor pressure of the solid state and the vapor pressure of the solvent state becomes equal, that particular point gives you the freezing point. Now, since the vapor pressure already decreases when a non-volatile solute is added to our pure solvent, automatically the freezing point also decreases. So, that is why we say that when we add a non-volatile solute to the solvent, there will be depression in its freezing point. Let's understand this by seeing a graph here. You can see the graph is plotted between vapor pressure and temperature. The first green line shown there is of the liquid solvent. You can see here that as the temperature is decreasing, the vapor pressure also decreases. Similarly, we can have a solid also. As the temperature increases, the solid starts to melt and acquire a liquid state. So here you can see that at the interjunction of the yellow and the green line, you have got a point, and this point refers or is equivalent to 1 atmosphere. That means this is the point which can be marked as the freezing point of this particular pure solvent, and it is marked as TF0. Now let's take our solution. Since the vapor pressure already decreases, the solution line lies lower, and you can see here that this line, the red line which is shown there, goes and meets to the point of the solid solvent graph at a much lower point. And when that is marked to the temperature axis, we will be getting the freezing point of the solution, which is marked as TF. From the graph, it is very clear to you that the TF is less than TF0, or the difference between the two can be given as delta TF. Now again, since this also is a colligative property, this delta TF also is directly proportional to the concentration of the solute present there. Now this concentration of the solute, here the unit considered is molality. Very similar to the previous one, isn't it? Exactly the same way we will be doing all the substitutions. Delta TF is equal to Kf into m, where Kf here is called as the molar depression constant or cryoscopic constant. The unit is Kelvin kilogram per mole. Same way we will be substituting the equation of molality as Wb by Mb into 1000 by Wa. And finally, we will rearrange the equation to find the molar mass of our solute, that is given as Kf into Wb into 1000 divided by delta Tf into Wa. Let's work out a problem here. A solution containing 34.2 gram of cane sugar with a formula of C12H22O11, which you already know, is dissolved in 500 cubic centimeter of water. This freezes at minus 0.374 degrees Celsius. Calculate the freezing point depression constant of water. Okay, let's jot down the given data. Here Wb, that is the amount of the solute, is taken as 34.2 gram. Wa, that is the mass of the solvent, is 68.4 gram. Now you may see that I have written it as 68.4 gram, whereas the data is given as only 34.2 grams. Now why I could write like that? You see that the 34.2 gram was dissolved in 500 cubic centimeter of the solvent. Now this 500 cubic centimeter, I made it into 1000 cubic centimeter. Then the amount dissolved also doubled. So we got it as what? 34.2 became double and it became 68.4 gram being dissolved in 1000 cubic centimeter. Now you already know that the density of water is 1 gram per cubic centimeter. So this 1000 cubic centimeter of water can be considered equivalent to 1000 grams. So you can say here that the amount of solute dissolved is 68.4 gram in 1000 gram of this solvent. Now coming on to the molality concept. 68.4 gram is dissolved per kilogram. 1000 gram can be taken as 1 kilogram. So 68.4 gram is dissolved in 1 kilogram of the substance. And now we have to divide that with the molar mass of the solvent. The molar mass of the solute. The molar mass of the solute, since it is cane sugar given there, or we can say that it is sucrose C12H22O11, is 342 gram per mole. Substituting that, we can easily calculate the molality, which is 0.2 molar. Now, applying the equation delta Tf is equal to Kf into m, you can easily find out that what is Kf, that is the molar depression constant or cryoscopic constant, which comes out to a value of 1.87 Kelvin kilogram per mole. This molar depression constant or the cryoscopic constant is for the solvent taken here as water. So, in this video, we have discussed the concept of what do you mean by colligative property. And though we had 4 types of colligative property to be discussed, I discussed only 3 properties in this video. That is, relative lowering of vapor pressure, elevation in boiling point, and depression in freezing point. The remaining topic of what is the osmotic pressure of a solution and how it is a colligative property, its mathematical application and so on shall be discussed in our next video. Hope the concepts are clear in this video. Thank you for watching this video.